Okay, so we will first begin with quantum phase estimation, which is used to estimate the eigenvalues of a unitary operator. And since the eigenvalues of unitary operator can be written as exponential power iota some angle, so this algorithm is also called quantum phase estimation, precisely because the eigenvalues of a unitary operator can be written as just a phase term because their magnitude is always one. So let me start sharing my screen and then we can begin. Okay, so let me begin with an introduction of unitary operators and eigenvalues. So when we have a general, operator or matrix A, we say that some column vector X is its eigenvector. If when you operate this matrix on this eigenvector, you get some scalar number and the eigenvector back. So this is called eigenvector and this is called eigenvalue. So in general, there are more than one eigenvectors and eigenvalues for a given operator. And if this, let's say, is a matrix of size n by n, then we can have up to n independent eigenvectors and eigenvalues. And in general, these lambda i's, these lambdas could be different. So in terms of notation, then we can use, let's say, xi lambda I xi, which means that I could be 1, 2 all the way to the size of this matrix. So if it is like a 2 by 2 matrix, there could be 2 eigenvectors and 2 eigenvalues corresponding to each of the eigenvector and so on. And in general, the method to find these eigenvectors and eigenvalues is this, that I can write this equation like this, lambda I times identity matrix. And if we can bring this to this side, so this becomes A minus lambda I equals 0. And for, for non-trivial solution of this equation, the determinant of this matrix has to be 0. For x to be not 0. And by solving this determinant, we can find various values of these lambdas, and for each lambda, we can then solve this equation and find xi. We won't be working with the lot of problems like this. So I'm not going to give an example for this. You can check out an example in some book on linear algebra if you are interested. So, but we are going to focus on a special type of matrices, which are unitary matrices. So unitary matrices are unitary transformations. They have this property that U dagger is equal to U inverse, which means that if I have unitary operator U and we take its product with its dagger, we get identity. And if we have a situation like this, let's see what is the properties of the eigenvalue. So if I have a unitary operator, which is applied to one of its eigenvectors, we can get some eigenvalues lambda I, and with the eigenvector lambda I. Now, if we take its dagger on both sides, so this will become U dagger xi equal to xi lambda I conjugate. And now if I, take an inner product of this and this side, we will get xi u dagger u xi equal to xi lambda I star lambda I xi. So this is identity because this is unitary. So this becomes identity xi identity xi, and this is lambda mod square, and this is a scalar. I can get it out. Now this is identity, so this simply becomes xi lambda I mod square xi. Now this is a constant number. This is a constant number, so I can cancel from both sides. So this gives me lambda I mod square is equal to 1, which means that the eigenvalue of a unitary operator satisfies this condition that the magnitude, its magnitude is 1. Not the value is 1, but the magnitude is 1, which means that if I, have a plane and I plot real of and imaginary of, lambda I on it, so the eigenvalues will fall on the circle with the unit radius, because the magnitude of any number lambda is 1. So this lambda mod is 1. So this is the condition that these lambdas have to satisfy, which also means that if I write this lambda I in polar form, I can write it like this. That since its magnitude is 1, this is exponential iota something, because its magnitude is 1. So this lambda I can be uniquely specified by this angle theta. So in this plane, this is this theta. So it means if I have different lambda i's, they will all have different theta i's. And in general, since theta and theta plus 2 pi give the same eigenvalue, I can restrict this theta between 0 and 2 pi, and this will still specify all the possible eigenvalues in this plane. So now I can write, eigenvalues of, actually let's use this index j instead of I, because I'm using I for iota. So these j eigenvalues where each theta j is between 0 and 2 pi. And actually some people, instead of writing this theta j, they can also write like this exponential iota 2 pi theta j. So in this case, this theta j has to lie between 0 and 1. And actually this is the way we will use it. This is, slightly cleaner when we will be using in our algorithm. Okay, so now let me specify what the quantum phase estimation algorithm is. So this QPE is an algorithm that say, okay, let's say we can do the unitary operator U. And actually not only this, but we can do its integer powers. Like we can do U1, U2, U3, and U4, and so on. If we can I find these eigenvalues so let's actually write this 2 pi theta j. So what are the theta j's if I have access to eigenvectors and this unitary operator U? So I have access to two things. I know the eigenvector and I know this unitary operator. Can I find this theta j? Can I find this eigenvalue? That's the this quantum phase estimation algorithm. And this is important in several situations, and also in simulating quantum mechanical system, because all these evolution operators, they are unitary. So this is what we are going to do as well, that we are going to find this angle theta j, which is actually related to the eigenvalue lambda j of the corresponding to the eigenvector xj. For now, I'm going to assume that we have a state where we are able to prepare this eigenvector purely, that somehow we have been able to come up with a state which is the eigenstate of the operator. But later on, I will show how we can find the eigenvalues when we don't have individual eigenvectors prepared, but we have a state which is the superposition of these eigenvectors. But for now, let's imagine that we have access to eigenstate and we have access to this unitary operator. So the algorithm for this actually is very simple. And let me just give the circuit right there and then explain why this circuit works the way we are saying that it works. Okay, so let's see the circuit. And suppose I have C number of qubits which start in a zero state, and then I perform a Hadamard transform, which essentially is a Hadamard on each of these input string. And then I have it like this. And then there is another set of qubits. So this is one register starting in 0. And this register, I'm able to start in the eigenvector state of the unitary operator xj. So this is xj. And let's say I use n qubits to represent this xj. And the algorithm is that I first do a unitary operator controlled by this least significant bit. And then I do another unitary operator, but which is u square instead of u. And this is controlled by the second qubit. And then I do u power 2, which is actually 4. So I do u4, which is controlled by this next qubit. And I keep going until I reach the last stage where I do a unitary operator raised to power 2 power c minus 1. And this is controlled by the last qubit. And just before that, if you want to see what is the one before, it's u power 2 power c minus 2, and this is controlled by just above. So this is how I have this series of unitary operator. I'll just prove a little bit later that at the output, I will still get the same eigenvector right over here. And then on these, C qubits, let's perform inverse quantum Fourier transform. And our claim is that at the output here, we will have a state from which I can measure theta j. This is the circuit. And let me show how it works now. Okay, so before I start describing the circuit, let me discuss one more thing. We know that if a unitary operator applies to eigenvector xj, I get exponential 2 pi iota theta j xj. But what happens if I apply u square? So when I apply u square, it is actually I can apply u to this. So if I apply u to this again on the left, so this becomes u square, and apply u on the right, I get another exponential 2 pi iota theta j. So they can both add up to make 2 theta j. And if I apply u cube, So I get 2 pi iota 3 theta j xj, and so on. So in general, if we apply u power x, so I get 2 pi iota x theta j. So whatever power is applied here, it actually is multiplied with this theta over here. And one important thing to note is this: we operate this unitary operator on eigenvector x. So at the output, we still have the eigenvector x. So this operator only modifies the global phase. So when it modifies the global phase, I can assume this global phase to be, present with the other state, which is in tensor product with this, if there is any. So that's why when this unitary operator is applying on this eigenvector, at the output, we can still rearrange things in such a way that this output is still xj. Okay, let me stop here and see if there is any question.
Sir,
Mm-hmm.
You said that we know the matrix U and we know its eigenvectors. So if we know the eigenvectors, then surely we have an idea of the eigenvalues as well, because we get eigenvectors from eigenvalues.
Okay. So, I'm sorry, I don't get the question.
I mean, earlier in the problem, you said that we know the matrix U and its eigenvectors.
Right.
And we have to find the eigenvalues. So if we know the eigenvectors, it means we had an idea of the eigenvalues earlier. That's how we find the eigenvectors.
Oh, so you're saying that we have found, if we do it in a classical way, you're right. So if we are working on a paper and a pen, and we know what unitary operator u we want the eigenvector and eigenvalues for, we will solve for the this equation.
The eigenvalues first and then the eigenvectors. Yes.
Okay, so we will solve this equation, and we will get x. We will first get the eigenvalue, then we solve this equation and we find x. Yes, you're absolutely right. So when we are working on paper, that's how we do it. And actually your question is, which you are perhaps a bit reluctant to ask, that why we are studying this algorithm.
Yes, sir.
Yeah, so just ask. That's why I'm asking you again, that you should ask the question. So the reason that we are studying this algorithm is twofold. Number one is that suppose somehow we know what this eigenvector is, and we know this unitary operator. So one way to do it on a classical computer is that you apply this eigenvector, this operator to eigenvector, and you can find eigenvalue. Okay, so you know this x, you know this a, you simply apply to this, and you will get your eigenvalue and eigenvector back. And the answer is this: whatever we are trying to do on quantum computer, we can do on classical computer. So but the point of using quantum computers is this, that we are trying to find algorithms that scale better than classical computer. And as you remember from our previous discussion, when we increase the number of bits, our this matrix A scales as 2 power n, which means that, so this is a column vector, which is like if this is like a single bit, this is 1 by 2, and I mean, so if this has a size 2 power n, this has a size 2 power n into 1. And if you want to find these eigenvalues, your computational problem is scaling as 2 power n exponentially. And if you know this n is 64, so you have a 64-bit representation numbers in this matrix. So that means we are like 2 power 64, and this is a hopeless task on a current computer. But on a quantum computer, we can do this task sometime, not always, sometime better than this exponential factor, just in polynomial number of terms, which means that we can get an exponential speed up over the classical computer. And the second thing, so this is one reason for doing this quantum phase estimation, that suppose we somehow know eigenvector already and we just want to find eigenvalue. And if our quantum algorithm gives us, a better scaling in terms of number of, bits, we will be able to find eigenvalues for larger unitary matrices faster than classical computer. The second reason is this, that sometime we don't even actually need to know the individual eigenvector for this method to work. At the end of this method, I will explain what would happen if we don't, have our state prepared in this eigenvector, but we have a state which is prepared as a superposition of these eigenvectors. In which case, I don't need to know this eigenvector, compute eigenvector beforehand. So I just have a state that I can quickly prepare as a superposition of this eigenvector, and I will be able to then find eigenvalue corresponding to each of this eigenvector quickly again. So
Yes,
Asaf, you get the point?
Yes, sir.
Okay, so and this is actually an important thing for other people as well. You see, whatever algorithm we are studying, if we are able to describe the algorithm, we can, write a program on a classical computer as well, and that will do the job because we know how to solve the problem. The only trouble is this, that some problem takes an awful amount of time, and especially as the problem scales, the requirement of computational resources on classical computers increases, much faster. And our hope of using quantum computer is this: if we are able to, come up with problems, not all, but maybe some problem that can be solved faster on a quantum computer than on a classical computer. So that's why we are studying all of this, and it's important to, keep this thing in mind. For example, one problem that we can easily see is the simulation of a quantum mechanical system. So if you have, a quantum system at some state size 0, you want to find, how does it evolve under a given Hamiltonian. So this is a unitary operator. So this problem on a classical computer requires exponential resources as the number of, particles increases. But we can, for many situations, we can implement this problem on a quantum computer more efficiently than on a classical computer. Okay.
Yes, thank you.
All right, so let's begin analyzing this problem, and that is that let's start discussing the input right from here. And at the end of this talk, I will also discuss some notational complexities that have crept up because of different notation by different people. And unfortunately, notation that I'm using are also different from Qiskit and Nelson and Chuang book a little bit. So we have to keep that thing in mind. But anyway, so for now we will keep following the notation that we have already discussed, that our least significant qubit is coming on top, and this is the one that we write on the right as well when we write the algorithm. So this is a 0 state which requires C qubits, and this is the eigenvector state which require N qubits. So our starting situation now is this. Let's say psi naught is starting in xj tensor with state 0. Okay, and after this first Hadamard. So this state, let me actually write it like this. So this is what I'm writing combined for N qubits, and for the remaining C qubits, I'm writing it each qubit separately. Now, when we apply the Hadamard onto this set of qubit, so it's Hadamard on this, Hadamard on this, each one is being Hadamard. So this becomes 1 over 2 square root 0 plus 1. So plus state. This also becomes plus state. So each state has become a plus state. So each of this line contains a plus state. And this is controlling this unitary operators on this eigenvector exchange. So let's see the impact of the controlled unitary with respect to the topmost qubit. So it's a qubit. So the topmost qubit is this one, and this is our eigenvector. So let me first, describe them separately, and then I'll get back to these ones. So if I find this one and this, I combine this one. So just the this part and let's say this 0th qubit. So this one I can write it as 0 plus 1 under root 2. So let's combine them. So this in combination I can write xj 0, xj 1, and there is a 1 over square root 2. Now, when I apply a unitary operator on this one, it's a controlled unitary operator. So unitary, controlled unitary, xj 0, controlled unitary, xj 1. So this is the control qubit, this is the target state, this is the control qubit, this is the target state. So this is 0, nothing happens to this. This is 1. So this U gate applies to this, which means I get exponential 2 pi iota theta j and the eigenvector state back. And now I can take this xj common again. And I have 1 over square root 2, 0 plus exponential 2 pi iota theta j 1. So it means that after this step, it's as if that nothing has happened to all of these qubits, and this phase has been modified. We have an exponential 2 pi iota theta j terms. Similarly, when we apply a controlled unitary operator with respect to the second qubit, the phase term with state 1 will appear as exponential 2 pi iota 2 theta j, and so on. And the final state, so this one will transform just until this point before the inverse QFT over here. This will become psi xj as it is, and this was the 0 plus exponential 2 pi iota 2 power c minus 1 theta j 1 tensor 1 over square root 2 0 plus exponential 2 pi iota 2 power c minus 2 theta j 1. The second last qubit 0 plus exponential 2 pi iota 2 theta j 1, and the last qubit 1 over square root 2 0 plus exponential 2 pi iota theta j 1. Is everybody okay with this thing? Ahmed Kirmani?
Yes, sir.
Perfect. So let me just say it again. So when there's a controlled unit between this and this, I get a phase term here. When I control unity between this and this, I get a phase term. But since this next unitary is u power 2, I get 2 theta j. Similarly, this last term has a unitary with a power 2 power c minus 1. So I get 2 power c minus 1 multiplied to theta j over here. So let me rearrange things a little bit. So this state is 0 plus. So let's take this 2 and multiply with this thing. So this becomes 2 power c theta j. So I have exponential pi iota 2 power c theta j 1. And you will see shortly why I'm doing it. So let's multiply with this 2 over here. So this becomes 2 power c minus 1. So 0 plus exponential, so let's write it, iota pi. And this becomes 2 power c minus 1. But let me just write 2 power c theta j. And the 2 power minus 1, let's bring it here. Similarly, you keep going. And the second last qubit becomes 1 over 2 square root, 0 plus exponential. So this becomes iota pi. So this, I also want to make this 2 power c. So if I make this 2 power c theta j, what has to come over here? So this is 2 power square. So it should be 2 power c minus 2. And the last term is 0 plus exponential. So this only 1, 2 is here. And I want to write exponential iota 2 power c theta j. So I write 2 power c minus 1 over here, 1. And I expressed it in this way because I now want to compare it with the Fourier quantum Fourier transform that we studied yesterday. If you go to the notes from yesterday, you will see that we did quantum Fourier transform of a state j and saw that it is equal to 1 over 2 square root 0 plus exponential iota pi j 1 0 plus exponential iota pi by 2 j 1, so on, exponential iota pi over 2 power c minus 2 j 1 0 exponential iota pi over 2 power c minus 1 j 1. So if we compare now this part and this part, we see that if this is nothing but a Fourier transform of a state 2 power c theta j, because this 2 power c theta j is coming where this j is coming in the quantum Fourier transform, which means that if I want to recover this 2 power c theta j, all I have to do is apply an inverse quantum Fourier transform on this part, and this will give me. So if I now apply a inverse quantum Fourier transform on this part, this will give me xj because this remains as it is. But on the right side, I have 2 power c theta j. So the first c qubit are transformed to a state 2 power c theta j, and these n qubits remain in the state xj. And now you also see that why the person who devised this quantum phase algorithm kept this particular choice of unitary operator sequence. Why it was u power 0, u power 1, u power 2, u power 2 square, all the way to u power 2c minus 1, u power 2c minus 1. Because with this particular choice of unitary operators, the state can be transformed to a quantum Fourier transform state of theta j. And now, as we did an inverse quantum Fourier transform on this part, this state was transformed back to the state of which it is an quantum Fourier transform. It means if I now make a measurement on this, I can find, so let's say, if I make a measurement on this state, whatever I measure would be this 2c theta j state. And I can recover this theta j quickly from the measured state by dividing it with 2 power c. Okay, any question on this? Okay, so let me now discuss what happens if we don't have xj prepared to operate unitary operator, but instead we have a state psi as a superposition of some, mu eigenvectors like this. And even in this case, it can quickly be seen that since this is just a superposition of eigenvectors, when this superposition of eigenvectors pass through this, the same operation is going to happen, and the eigenvalues are going to be multiplying with individual eigenvectors, which means that at the end of this algorithm, this state will transform to the superposition of 2 power c theta j. It's now mean that when I measure, the measurement can generate a histogram. For example, there are 3 eigenvectors which were prepared in this superposition. So I have this probability of measuring this state, let's say c1 mod square. So this will be 2 power c theta 1. So this will have a probability, the second eigenvalue has this probability c2 square, this has probability c3 square, and 2 power c3. But for the purpose of finding the eigenvalue, all I'm concerned with is finding this state. What's this state? So whatever state is showing up in the measurement, I can use that state to find the corresponding eigenvalue. So even if we don't have a state prepared in one of the eigenvectors, if it is in superposition, we can still use the same algorithm, and we will be able to find multiple eigenvalues right there without actually knowing the eigenvectors. Okay. Perfect. So let me now discuss its implementation in Qiskit. So for Qiskit implementation, I have taken a very simple unitary operator. It's a single qubit unitary operator, and it's actually the phase operator. Because I'm preparing it in a simple way to make a check. So I'm preparing a unitary operator actually in a certain way that I can quickly find its eigenvalues right there. So if I have a unitary operator like this, a single qubit operator, let me first find its eigenvalue, eigenvector before implementing it in Qiskit, so that we know if our Qiskit implementation works fine or not. So for that, you can check one thing, that if I have a state 0, 1 and I apply unitary operator to this, let's see what happens. Instead of actually finding the eigenvalue, the eigenvector, let me just check if the state that I'm giving you is one of those or not. So 1 into 0 is 0, 0 into 1 is 0, 0 into 0 is 0, exponential 2 pi iota theta into 1 is exponential 2 pi iota theta. So this is 0 exponential 2 pi iota theta. And let me take this thing common. So exponential 2 pi iota theta 0, 1. Perfect. So it means that this is an eigenvector. And its eigenvalue is this with a phase theta. So whatever theta I specify in this unitary operator, it's appearing as the phase that I want to measure. So this is a very nice way of checking the implementation of quantum phase estimation in Qiskit, that I prepare a unitary operator with a which has a parameter theta, that when I measure I should get that parameter back to when I prepare my state in this 0, 1 state. And let's see what's the other state. So this is the one this is the 0 state. Sorry, this is the 1 state and this is the 0 state. So if I have my qubit prepared in 0 state, let's see if this is an eigenvector or not. So 1, 0. So 1 into 1, 1, 0 into 0, 0, 0 into 1, 0, this into 0, 0. So this is my eigenvector. So I can easily write it exponential 2 pi iota 0, 1, 0. So it means I have this eigenvector with the eigenvalue this with phase theta, and I have another eigenvector. It's an eigenvector because when I operate with u, I get it back. And this is as if I get it multiplied with 1, and 1 can be written as exponential 2 pi iota into 0. So it means this has an eigenvalue 0. So if I prepare my my input state in this vector, I should get phase theta. And if I prepare it in this vector, I should prepare a phase 0. And can you guess what would happen if I prepare my x state in this eigenvector? Sorry, this is not an eigenvector. But if I prepare it in this state, you can easily see that this is equivalent to 1 over under root 2, 1, 0 plus 1 over under 2, 0, 1. So it means at my output, I should get a histogram with 2 bars, and their index should give me both of the eigenvalues right in a single operation. Any question before we head off to Qiskit? And you can easily see one more thing, that this unitary operator can be implemented with a phase gate. And if I want to implement control unitary operator, I can implement with control phase gate in Qiskit. And also, if you want to implement a unitary operator with some power, 2 power p, all you have to do is in this phase gate, apply this 2 power p with this phase term. So its implementation in Qiskit is actually very, very straightforward. Perfect. So let's now see its implementation in Qiskit. Okay, so let me share. Can you see the notebook? Is the notebook?
Yes, sir.
Yes, sir. Yes, sir.
Okay, perfect. Thank you. So we start with this, usual import of desired functions. And then I have a simple circuit. You see a quantum circuit with n+1 bits. So this n is what I was actually calling C before. So actually, let's write it C so that we can match it. So I'm using C for counting. So these are counting qubits. They're not the qubits that are required to And actually, let's say n is equal to 1. So we have n qubits to represent the unitary operator or eigenvectors, and n qubits for eigenvector representation and c qubit for counting. So this is where I set the initial state. So this is, if it is 0, 1, this is one state. If it is 1, 0, or whatever state you want. And this should be set on the last qubit, which is in this case c plus n minus 1. And then this is the theta that I'm specifying for verification purposes. And you see I'm beginning with the applying the control unitary operation, and I have sorry, this is x. So this is the way I'm defining exponent, and this should be c plus n minus 1, because we are applying this control unitary operation on the last qubit. And for IQFT, I'm this time using a function from Qiskit, which is implemented there. We can actually use the function that I made also, and it works exactly the same. And let's say we have the C. Let's see if it works. Perfect. So now you see that I'm implementing a control unitary operators on this state psi, and they're all phase gates with the this exponent that we are defining 2 power c minus x minus 1, and this actually works the same way. You might notice one thing, that when x is 0, this first qubit, when I was explaining the algorithm, I had taken this to apply for just the unitary operator u with power 1 and exponent x0. But here I have done it in the opposite way. So for the next one should have been unitary operator raised to power 2, but I'm starting, I'm not implementing, like this. So this is the way I had explained in the lecture, that let's apply with the exponent with 2 power x, where x is the index of the qubit. So 0th qubit 2 power 0, the first qubit 2 power 1, and so on. So each time this angle is this phase is increasing. And the reason is this, that in Qiskit, this q4 qubit is actually when it is measured, it's placed on the right side, and this q0 is placed on the left side. So because of this opposite thing, I am defining this circuit in the opposite way as well. Anyway, so this is why I have these powers in reverse, because of Qiskit's convention. And now once we have done this, let's run it. And you see in the simulation, I'm getting all of the simulation data. Now I have prepared my final state, my state in this 0, 1 state, and this is the vector with a particular eigenvalue. Can you guess what was the eigenvalue that we had said this 0, 1 should have? Can you tell me what did I just wrote in the notes?
Sir, exponential to the power iota 2 pi theta.
So it's good. So the eigenvalue is to e power 2 pi iota theta, but the phase is theta. So for this, I should get the phase theta back. So how do I get it? The way is that I see which is the state which is coming with the highest probability. It's 1, 0, 1, 1, 1. And you see these other states, because of because of the approximation errors to represent this value point theta using these 5 qubits that we have specified. But anyway, let's choose this highest probability. And since When you will be using a lot of qubits, it will become harder. So what you can do, you can use this command to find out the highest probability outcome. So it actually takes this counts, and from counts, using this, operator command, you can find this highest probability outcome. And this is, in this case, 11101 state. So this 1101, you can convert it into integers using this int command, and specifying that this string is actually in binary, and then you divide it with the 2 power c. 2 power c is the number of counting qubits, and this is the theta that we have measured. So it should have given us 0.9, but it's giving us 0.90625, because number of qubits c that we have used to accurately represent 0.9 is not enough. You can get a better approximation by increasing c. Let's say we increase c to 6. And it's still not close, but 0.9, what was the previous value? 0.90625 is now.
I think it is the same.
Okay, so let's make it
965.
so now I have made 4. So because it's rounding as well, so it's not showing the decimals after that. So it's easier to compare for smaller c. So for c is equal to 4, we are able to get 0.875. And if we increase the qubits to 5, it it gets better. So it keeps getting better if you keep adding the counting qubits. Okay, let's also check.
Sir, could you please scroll down? थोड़ा सा और,
Yeah.
sir. Yes, this in 21 line. Highest probability outcome इसके साथ जो ये 2 है.
So this is telling us that this string 1101 is in binary scheme. So this 2 is specifying the base for this number, and then it's converting with this information and this into integer.
So that would be a decimal integer.
Yes, so this is in decimal. So this is the value in decimal, and then you divide by 2 power c.
Okay, sir. Thank you.
Perfect. So let's change to the other state. Let's say make it 1 0. This time the answer should be 0. And you can see that measured theta is 0 because it's the highest probability state is 0. So there's only one column. And let's say what I said about this state divided by np.sqrt. So actually, we are getting both answers now. So the way this bottom part is set up is not set up to handle these 2 outcomes. So both of these are 2 states that are showing up, and we can see that this has this index 10111, which actually when Qiskit will read it would be 11101, and this is the same one that before. And then now we also have a high bar at 0 0. This corresponds to one eigenvector. This corresponds to the second eigenvector. So now you see that I haven't specified my state in any of the eigenvectors, but as a superposition of 2 eigenvectors, and it is still able to find the phases for both of them over here. Okay. So any questions on quantum phase estimation? Perfect. So let's take a 10-minute break, and then we will study another algorithm. It's called quantum counting.
सर आप चार्ट देख सकते हैं प्लीज